So hello and welcome to today's webinar about hybrid engine measurement. In today's webinar, we will go through what is a hybrid engine. I'll explain different powertrain types that are used in hybrid engines. We will see how to measure in Dewesoft and what is required to do the measurement. And then we will go to Dewesoft and actually do a measurement using this small demo engine. So this is a small-scale full combustion engine coupled with an electric motor. Basically, it's basically a model of an actual hybrid engine. So we can do complete combustion analysis and complete power analysis on the engine. I would also suggest going through the webinars in our webinars archive. So we have had one webinar for combustion analysis and one webinar for power analysis. And this is basically joining those two things together in one measurement. And the webinars are also available on our webpage in the Pro Trainings section. So what is actually a hybrid powertrain? Hybrid powertrain is a combination of an internal combustion engine and an electric motor, as you can see here. So we have a combustion engine and an electric motor, and the way they work is they can at some point work together to give you full power or additional power if you need to overtake, accelerate. Only one can work by itself. For example, if you're driving in a city, then usually the electric motor can move the car or starts moving the car because it's more efficient from going to zero velocity to start to the moving speed. Or only the combustion engine can drive the car. For example, if you're driving on the highway, then the battery doesn't last long enough and the combustion engine needs to take over. So we have different operation modes of a hybrid powertrain. And also in this webinar, we'll be focusing on powertrains that have an internal combustion engine. This can be either diesel or gasoline, coupled together with an electric motor. So there are also other hybrid powertrains like hydrogen engines with electric motors and so on, but in this one we'll be focusing only on internal combustion engines with an electric motor. So we have different powertrain types, most common being electric internal combustion engine with an electric motor, and they can be coupled in parallel or in hybrid. So if they are in parallel, it means that the combustion engine and the electric motor can both drive the vehicle at once. So they're basically mechanically coupled to the wheels, and both of them can give out electric or mechanical power to the same pair of wheels. The combustion engine in this case drives the wheels through the transmission, and also the electric motor is then driven through the same transmission. If we have a series hybrid vehicle, it means that we have a combustion engine, which is basically a range extender, and it drives the electric generator. So we don't have a mechanical link between the combustion engine and the vehicle. So we drive the electric generator, which generates electricity, and it charges the battery pack. And from the battery pack, we then power the electric motor, which drives the wheels. So this is common with vehicles that have in-wheel motors, and we don't need to have any transmission in between the engine and the vehicle. So the requirements for doing any kind of measurement on hybrid powertrains are similar to using a combustion analyzer or doing power analysis. So for a combustion analyzer, we need to have one angle sensor, on the crankshaft of the engine, and we need to have one pressure sensor on the engine to measure the cylinder pressure. So in this case, we are using PSG. So this is pressure sensor glow plug. It's actually a glow plug with an integrated pressure sensor. In this case, we don't have the spark plug mounted because we cannot do actual combustion in this room. So we are only measuring pressure with this pressure sensor glow plug from a Slovenian company, Hydria. We are also doing power analysis on the electric motor. So we have a three-phase electric motor. We maybe try to move this a bit closer. So we have here a three-phase electric motor, an inverter in the box, and we have a DC power source. So this is basically your battery. And we are measuring current on the DC power source with the current clamp. We're measuring also voltage on the DC power source. And then we are measuring with these three power current clamps, also the current of the electric motor. And we are measuring all three line voltages of the electric motor. So we have complete analysis of the powertrain, basically same as it is in any vehicle. The only difference is that in vehicles we have usually only one combustion engine, but we can have multiple electric motors or either multiple batteries. So we can just multiply the amount of channels we need for power. For combustion, it's basically the same, but we can have multiple cylinders, so either 3 or 4 cylinders, usually for a smaller combustion engine. So how do we do the measurement in Dewesoft? We basically use a combination of power analysis and combustion engine analysis. So the module for combustion analysis has just recently been completely redesigned, and it has additional functionality for any new engine. Also, the power analyzer has gotten new updates, new calculations. So both modules are really top of the line on the market and are capable of doing hybrid powertrain analysis. The biggest benefit of doing this analysis with Dewesoft is that we can do only one measurement for a complete powertrain. Of course, there are on the market other combustion analyzers, other power analyzers, but there are not many systems that can do one measurement for the complete powertrain. And this is really important once we integrate the complete powertrain together. So usually only the electric motor is being developed up to a certain point, and the combustion engine is being developed by itself. But when we put the system together, we need to also measure if it is working together as it should be. So we can have at the end of the measurement only one data file for the complete powertrain, and we can use the same hardware for both. So here we have a really nice example because we don't have any dedicated hardware. We basically just have 2 slices with different kinds of inputs. And we have connection of 4 voltages. So here we have only 15 volts input. And it depends on the battery source, what kind of inputs we need. So if it's an 600 volts or 800 volts battery, then we need high voltage inputs, which can go up to 1000 volts. Or in this case, we can just connect them to any ACC input or SDG input via an adapter, and we can connect the banana cables directly. In this case, we are also measuring 4 times current. So the current clamps are powered directly from the modules. We need, in this case, 4 times low voltage modules to power the voltage clamps directly. They have also test chips inside. So as soon as we connect the current clamps, they are detected all the scaling is set, and we can immediately start measuring. The cylinder pressure sensor is connected to an STG input in this case because it needs to have voltage or excitation, and it has also linear voltage output. We have also on these slices charge inputs, so if you would have a charge type sensor, we could also connect it directly without any external amplifier. And we have on the back side of the engine, we have an encoder mounted, which is connected to the counter input. We have, of course, also possibility of analog input connection of the angle sensor. And on this engine, we have two additional sensors mounted, just as an interesting fact. So one accelerometer on the combustion engine, and we have here also one microphone, so we can measure the noise of the exhaust that the engine makes. So now we'll switch to Dewesoft and see how the measurement is done inside Dewesoft. Okay, so we'll start first with the analog inputs. We have here different types of inputs. So we have two slices connected together, which are synchronized with one sync cable in behind. And you can see that the size of the system is really small. So it is one of the smallest combustion power and hybrid analyzers on the market. It's really easy to put this into the vehicle. Of course, it's also meant for use in the laboratory, but it's a perfect fit also for any vehicle, which you can just connect either to a laptop or to a Dewesoft measurement computer, which adds also additional ruggedness and safety. So we have here 4 voltage inputs, so 3 phases of the electric motor. Then we have also voltage of DC power, so the battery or the DC power source. We have also 3 currents, so the current clamps for the electric motor. And at the end, we have also current of the battery or the DC power source. We have also connection of the cylinder pressure connected, and we have one counter or angle sensor connected. So this is an encoder with 128 pulses. And if we turn the engine, so we can see it moving. And in our case, we have also one accelerometer and one microphone. So these are both IP inputs, and they are detected automatically. So what we needed to set up for this measurement is the combustion analyzer. So first we added the combustion analyzer. We set the engine type, fuel type. We need to input the geometrical information of the engine. So this is 25 cubic centimeters displacement engine. So it's a really small engine from a weed whacker. And we have only one cylinder measurement. For the encoder settings, we didn't have the encoder 128 on the list, so we just created an additional sensor. This can easily be done if we go to options and editors. We have counter sensors, and we can create any type of new sensor. So for example, if we would have an encoder 256, we could just create a new sensor, select encoder, and select the number of pulses per revolution. So after we save the sensor, it's immediately available in the list of sensors. In this case, we are still using the 128, so we will leave the sensor. We can select the resolution of the angle sensor, And after that, we have valid outputs for the combustion analyzer. We see here one warning. So angle and pressure channels must be on the same slice for correct TDC detection. This means that if we want to do top dead center detection, to detect how far off the angle sensor 0 point is from the actual top dead center of the piston, we can do automatic TDC detection if we don't have any firing in the cylinder. So in this engine that only has compression, that we only measure compression, we could do this TDC detection, but we have to make sure that both the angle sensor and the pressure sensor are on the same slice, because we are doing TDC detection in channel setup. So in channel setup, the slices are not synchronized. They are only synchronized when we go into the measurement. So this means that if you would have the pressure sensor on the other slice, we could have some delay between the signals. So when we go to measurement, then all the slices are perfectly synchronized. For the TDC detection, we need to make sure that they are on the same slice. We can also move them just for this measurement and then move the inputs. So at the end, we just need to enable the outputs that we want to see, and our combustion analysis measurement is ready. For the power measurement, we have here two modules. So one is the power analysis of the three phases. We selected three-phase delta wiring for the electric motor, and we just need to link all our channels for voltage inputs and all our channels for current inputs. We need to also select what is the nominal voltage of from line to line, and from where we get the frequency source. So this has variable frequency, and for this we can select the voltage source and one of the phases to calculate the frequency of the lines, because here we have variable frequency because we are using an inverter. At the end, we just need to select the outputs that we want to see: power, energy, power quality, and we also have the vector scope preview when the engine is turning, so we can check if the wiring is actually okay. We have added another module for measuring only DC power. So in this case, we select only DC voltage and DC current. We can select the outputs of the units, and we can calculate the energy. So it's also a really simple setup to do analysis of the battery. Now, this combustion engine is basically powered by the electric motor, and it is run by an RC inverter. So the inverter is from a small model airplane, and we need to also drive it somehow. So we did this with the function generator, because this inverter needs a 50 Hertz square wave signal, where the length of the pulse changes from 1 millisecond to 1.5 milliseconds. So we are using the analog output on one of the series slices, and with math we have generated a frequency of 50 Hertz, and then one sawtooth signal where we can change the width of the pulse. So we change width of the pulse with one user input. We basically have just a slider in the setup, and we can change then change the pulse for the output, and we can change the speed of the electric motor this way. So let's give this a try. We go to measurement. So I already prepared one measurement screen. Let me just make this a bit smaller. So it might be that the motor will be a bit loud, so I hope you can hear in between. I'll just make a short measurement. Okay, we'll go into analysis mode so we can see what we have measured here. We don't need this image at the moment. Let's just zoom into a part of the data file. So just to explain what we have on the screen. So the slider that I moved, this changes the poles for the PWM output for the inverter, and we actually drive the engine this way, so we can change and control the motor from Dewesoft directly. Then we have here calculation of DC, so of the battery or the DC power source. We have the voltage, current, power. Then we have complete analysis of the electric motor. So all three phases are shown here. Let me just reduce the size of the text so it will be a bit easier to see anything on the screen. So we have all three phases. So here we have the RMS voltage values between the phases. We have the current between the phases. And since we do complete analysis of the DC power source and the AC power source, we can also calculate the inverter efficiency. So what are the losses between the DC power source and the AC power source? So what is the efficiency in percent? What is the actual power loss that is basically heat dissipation from the inverter and the motor? We have complete harmonics analysis of the electric motor. We have all three voltages, currents available in the time domain, and we have also the vector scope. So, and here on this side, you can see a complete combustion analysis. We have measurement of the cylinder pressure in the angle domain. So here, cylinder pressure might seem a bit strange, and that is because we are only measuring compression and expansion without any combustion in the cylinder. So we are, it's basically acting as a compressor, but still we can see all 4 strokes of the engine, and we have the actual shape of the pressure signal in the combustion. And we can also see that we can also evaluate pressure in the angle domain. So move as we are changing the velocity of the engine. We can also see a change of the pressure inside the cylinder. So here is when we reduce the velocity. We see also a decrease of the pressure in the engine. And we have also then calculation of power in the engine, maximum pressure, position of maximum pressure, what is maximum rise. We have calculation of mass fraction of fuel being burned at different points. And we can see that in this data file, we can actually combine both of these things together. So what is the actual benefit of Dewesoft? This is that we can also put power values into combustion analyzer screen. So if we go to combustion analyzer. We can add additional channels to the cylinder, and we can, for example, add the voltage and current channels to combustion analyzer. And now when we go back to the data file and recalculate, so we can do everything also offline as long as we stored all the raw channels or all the analog input channels. We can just recalculate the data file and do modifications like this, like adding additional channels into combustion analyzer or doing calculations in mathematics between these channels. So we'll just recalculate the complete data file. This takes a bit of time because we have high angle resolution of combustion analyzer, and we have also high frequency calculation of the power analyzer. And also the data file here is a couple of seconds long. So the benefit is that we can add now voltage and current channels to the power analyzer, and we can see how this looks like in the angle domain. Let's maybe leave just the power or just the voltage channel. Put this to 20 volts, from -20 to -20. We can see also how the voltage is changing when we change the RPM, and we can see this in combination with the actual pressure. We have here also measurement of sound. We have one microphone, and if we put this as an additional channel, we can also evaluate this in the angle domain, and we can also see the exact point of the exhaust valve opening. So the microphone was closer to the exhaust, and we can see this when the exhaust opens after the combustion phase. We can see also an increase in the sound, and we can also correlate if we are doing measurements on different positions of the engine where the noise is coming from, and in which position we have this high pressure or an increase in sound. So this is a really simple measurement of a complete combustion and electric engine. The data file will be available also online for later analysis, and this shows just basic functionality that can be done in Dewesoft. Of course, there are much more options that can be added, like doing complete mapping of efficiency of the motor. So we have scripts for mapping the efficiency at the different RPM and load of the engine, and we can evaluate in which positions the engine also has the highest efficiency, the highest fuel consumption, and so on. So with this, I would conclude today's webinar, and I thank you all for your attention.